idea exactly goes. It's not a corollary. The idea is the same for this part one. This is an interesting statement. How you write down some continuous thing, and it's always differential. What is it? Antiderivative always exists. That's what that is. So here's a proof of fundamental theorem, complex integration, part 2. And again, I think I'm requiring, for ease of the proof, the assume U and V are continuously differentiable. That we can only play with this differential algebra and not going into topological argument. All right, so let's see. And we have this property. Let me see how I start. Starting from here, C Fz dz, this being 0, that's the property that we're starting with, right? It has path independence, and we can define a function, but let's break that up into two parts, dr plus I dr and C. There's some vector field in there. If you look at this idea on above, and we already know this is a gradient vector field, right? It's a gradient vector field using phi. So we can write it, this is a gradient vector field notation. Okay? Delta phi. And there's another gradient vector field, and dot product to the vector dr dt, shorthand notation like this. Goes like that. And then what is the fundamental theorem of line integral by looking at it here? Fundamental theorem of line integral. Wasn't that phi of, let's say point A to point B, right? That was a phi B minus phi A. Remember, starting and ending. And this is a potential function. It doesn't matter how you go, only the beginning and terminal point ends in there. So I times psi A to B. So also I'm doing this maybe in the wrong order. I'm sorry about this. The Fz is defined like this: gamma, starting from initial position to somewhere, Fz dz, and whether this is 0 or not, this is always broken into these two parts. So here's the phi z. Wait a second. Let me. If you look at this process, it goes exactly like this: phi z 0, z plus I psi of z0 and z. Here, everything is in terms of real, but I'm abusing the notation here and entering complex x plus iy and notation in here. So, what is this one here? Phi of, oh, we're right. This is phi of I plus psi z0 and z. That's what f of z is. So using that property, the path independent property, broken into real part and imaginary part, enter this conservative vector field. Using those conservative vector field for real part and imaginary part, I could actually write that function fc that is defined in here, like this. Does that make sense? And all I have to show is that this phi and psi, f is analytic, show is analytic, and its derivative, therefore you can consider the derivative. Derivative is whatever we want it to be, right? So how do you show it's analytic? Show f is analytic. This is like u and v, right? This time, the real part and the imaginary part is phi and psi. Why is this continuously differentiable? What is the name of a phi x? If you go back to this earlier context. was u, and phi y was negative v, right? That's the same context. Are these continuous? These are continuously differentiable, is in particular is continuous. And the same thing, phi x and phi y are v and u, and they're continuous. So this part, real part and imaginary part of the newly defined function, has continuously differentiable real part and imaginary part, right? Then what is the next part to finish off this analytic? You have to show the Cauchy-Riemann equation, right? What's the Cauchy-Riemann equation of a phi and psi? Phi x is u, and what do you compare that with? Is that psi y? That is also u? Well, here's it's all written, and it is true. How about the other one? Phi y versus psi x, right? What is the phi y? Negative v. What is the other one? Psi x here? V. So are they in opposite condition? Correct? So these two functions, phi and psi, satisfies what? CRE. This real and imaginary part is continuously differentiable and CRE, therefore it's analytic, right? Okay, it's analytic. What's next? We show that function that's defined in this way is analytic, and we actually calculate f prime of z. I started today's course with how to actually calculate f prime of z in terms of a partial derivative. It was a g, right? So let's write it again. F of z now has this real part and imaginary part. What is f prime of z? Remember that part? You don't have to look at complicated direction. Only one direction is our answer to this one. All the other direction is you wind back. So what is the direction that you don't have to wind back? X direction, right? So what was the answer here then? Derivative with respect to x, right? Plus with respect to x. Is that right? You don't have to look at other things. But what is phi x? Is that u? Phi x is u. What about psi y? Psi x? Psi x is v. So if you differentiate that, you get u plus iv back. So fz is defined. We show this analytic, and its derivative is the given function u plus iv. Therefore, we prove that the function defined in that fashion is an antiderivative. How many antiderivatives are there? Infinitely many, right? And if you look at the definition of this choice of our function there, this is your choice. When you define this one, this is your variable, but you can begin anywhere. Z0 here, Z0 there. That'll give you constant difference. Okay? So I'll stop here.